Alright, today we're going to talk about the rock cycle. You should have a sheet that looks like this. If you don't have one, go and find yourself one or draw this on a blank piece of paper. Okay, somewhere up here at the top, just write yourself rock cycle. And we'll get started. This is 10.1 in your textbook. Okay, so the rock cycle is kind of unique in the fact that it doesn't follow a set pattern of events. A lot of times with a cycle like the water cycle, you get evaporation, condensation, precipitation, and it kind of goes in a set pattern. It is a true cycle, but it goes in a set pattern. The rock cycle, even though we're going to learn it kind of in a set pattern, at the end I'm going to show you that there are a lot of other options, okay? And the main reason that a rock could go through many different sequences of events all boils down to one key factor, and that is location. So where the rock is located or moved to a new location will determine the path it takes through the rock cycle. Okay. The other big thing to remember with the rock cycle, being that it is a true cycle, that means that it repeats itself forever. Okay. So even though we're going to change the way the rock looks, maybe some of its basic physical characteristics, chemical characteristics, it still is never destroyed. Okay, so that follows the principles that matter is never destroyed. Matter can be changed, but matter can never be destroyed. So some of you might argue that, well, when you melt a rock and turn it into magma, you've destroyed it. When in reality, all you've done is change it from a solid to a liquid, right? You've just changed the state of matter, but you haven't destroyed matter. So molten rock is just a different state than, for example, an igneous rock, okay? Just solid versus liquid, okay? So matter is not destroyed. Therefore, the rock cycle has been going on for, 4 billion years and will continue to go on for another 4 billion years just with changing of rock from one form to another. Okay, so we'll start down here at the bottom, kind of at the beginning, if you will, and you're going to write magma and lava in that spot. So you got your molten rocks, right? Remember the difference between magma and lava is that magma is underground and lava is above ground. Okay, so when magma or lava cools, so the process you want to write here is cools and hardens, okay, it's going to form crystals. And those crystals are going to form a rock called an igneous rock. Okay, for example, like granite, very popular rock in our area, is an igneous rock. So it cools and hardens, forms igneous rock. Now, as we learn with minerals, where that rock cools and hardens will determine the size of the crystals in the rock. So we know that magma is down in the earth. It's going to cool slowly, and it's going to give us large crystals, which means we can see them with the naked eye. We don't need any magnification. If it cools a little quicker, like from lava, for example, we're going to get small crystals. Okay, so again, size of the crystal is dependent upon how long it took to cool. Now, in some cases, this is where an igneous rock would differ from a mineral. We can actually get rocks with no crystals. They will have no crystals because they form that fast. So think about maybe like the Hawaiian Islands. The lava runs down into the ocean. It's contacted with the ocean water. It cools within seconds to maybe just a couple of minutes. It forms so fast, it hardens so fast that crystals don't have time to form. So therefore, when you see rocks like pumice, which is the rock with all the holes in it, or obsidian, which people call volcanic glass, those have no crystals in them whatsoever because they form literally in seconds to minutes. No crystals had time to develop. So you're going to get large crystals from magma, smaller crystals from lava, or even no crystals from lava if it cools that fast. Now let's say that that igneous rock perhaps maybe cooled off at or near the surface of the earth, or somehow it was brought to the surface of the earth. Now, of course, it's going to get rained on, snowed on, ice, wind, all the processes that wear a rock away that we call weathering. Okay? So it's going to get weathered. It's going to get broken apart into pieces. Okay? And then, of course, we maybe get a heavy rain, or if the pieces are small enough, wind can blow them around, or maybe we get some spring thaw and it floods and we move large quantities of pieces of rock that have been weathered. And when we start moving those pieces, that is called erosion. Okay? Now, the pieces themselves go in this spot up here, and those are called sediments. Okay? So sediments are really nothing more than pieces of rock. And those pieces can be anywhere from the smaller than a grain of sand all the way up to baseball size, softball size, grapefruit size. They can be quite large. They just have to be a piece of the original rock. So if we have a rock that's this big, if it breaks a chunk off that's this big, that's still technically a sediment because it is a piece of the original rock that has been broken off. Okay, so rocks get weathered, they get eroded, we call that sediments. Typically what happens when erosion takes place is those rocks are going to move themselves down into lower land areas, valleys, and most importantly into water. And when they get into water, whether that be a small stream, a big river like the Mississippi, a lake, the ocean even, that sediment, those rocks, will settle their way to the bottom. And they will begin to form sedimentary layers, because as a layer comes down, more rock will pile on top, pile on top, pile on top. Okay? Then we have the beginning of a process called compaction. Right? Right? Think about those sedimentary layers are going to get compacted. Okay? So as more and more rock layers pile on top, more sediment piles on top, it pushes those layers down, and instead of them maybe being this thick, they'll get squeezed down and be only that thick, okay, because they're being compacted. Now eventually they're going to get buried deep enough that the water, maybe the bottom of the lake is way up here now, and this bed down here actually will dry out. So now we're removing water. And we know from our lab that when we remove water from a solution, it leaves behind the mineral. Okay? And in this case, that mineral serves as a cement. That process is called cementation. Okay? But if you can remember that it gets compacted and cemented together or glued together, you should remember these two words. All right? So the deeper it gets, the more compacted and compressed it gets. And then once it dries out, the mineral left behind, will cement that rock together. Okay? So compaction and cementation, and now we end up with a sedimentary rock. Okay? Sedimentary rock is simply a rock made of sediments, pieces of other rock. Okay? Sometimes they're not even that tightly packed together, and if you find a sedimentary rock, you can take your hand and you can rub it, and you can actually get the sediment to fall right back off. Because remember, it's only glued together with some minerals. Some are harder than others, maybe depending on how much they were compacted to begin with, or maybe depending on the type of mineral gluing them together. But it's simply sediments being glued together. Now when we get into talking about big lakes and oceans, where you get a lot of living organisms in there, especially like an ocean, you get a lot of living organisms that are dying constantly and sinking to the bottom. Same process, but now instead of the rock being made from sediments, okay, that rock is being made from dead material. So now we would call it an organic sedimentary rock. Okay? Whereas this one's made from rock pieces, an organic sedimentary rock is made from dead stuff. So you're going to find bones, shells, fossils of some sort in it, maybe plant remains, maybe the impression of a plant, things of that nature. You're going to see things like coal, for example, is made from plants. There are varieties of limestones that are made from just simply shells and dead stuff that has made its way to the bottom of the ocean. Chalk is made from microscopic organisms that they find on the bottom of ocean floors. Okay, so you get a couple varieties of sedimentary rocks, whether they're made from pieces of rock or from organic material. And then the third type of sedimentary rock would be very similar to what we did in our lab when we had a solution where we had water and salt. We removed the water and we made salt crystals. That is how rock salt is made. And there's a variety of limestone that's made the same way through the process of evaporation. So again, you have a liquid solution, and in that liquid is a heavy content of dissolved mineral, whether that be salt, for example. And then when you remove the salt or the water out, you leave behind the salt. We call that rock salt. That is called a chemical sedimentary rock. Okay, so we have three types of sedimentary rocks. When we talk about sedimentary rocks, you're going to be able to, you think, okay, is it made from pieces of rock? Is it made from dead material? Or do I see maybe some crystals, like maybe a grain of salt, and therefore I might think that it's a chemical sedimentary rock. With igneous rocks, you really only have two things to think about. Do I see large crystals or small crystals? Then you're going to know whether it was formed in the ground through magma or out of the ground through lava, simply by looking at the size of the crystal. Okay? With the sedimentary rock, there's a little more involved because you got to think, what is it made of? Pieces of rock, crystals, or dead stuff, organic material. Okay? All right, so now we have the sedimentary rock that's buried deep down below a riverbed, lake, ocean. Okay? If that rock continues to get buried deeper and deeper and deeper and deeper in the earth, we know that as we go down deep into the earth's crust, it's going to get much hotter. So it's going to be subjected to a lot of heat. Okay? Now, we also would then suspect that since it's getting buried deeper and deeper and deeper in the earth, it's going to have a lot more pressure pushing down on it. Okay? In fact, it's going to have so much heat and pressure on it that it's going to go through physical and chemical changes. So we're literally going to change the rock into something that looks completely new and different. Okay? And if that happens, we get what is called a metamorphic rock. Okay? And I want you just to remember back to life science where we talked about metamorphosis, right? You got the caterpillar that turns into a butterfly, right? Metamorphosis. Looks nothing like the original, has gone through a complete change from the original. Metamorphic rock, same concept. Okay, we take a rock, it goes through so much heat and pressure that it turns itself into a new rock. Okay, metamorphic. In fact, it has so much heat placed upon it that it should melt. Okay, these rocks, the temperatures for these rocks actually go beyond their melting point, but because they are under such immense pressure, they don't melt. Okay, same concept holds true if you were trying to get water, to keep water from boiling. So we know that water boils at 212 degrees Fahrenheit. So if I have a regular pot and I heat it up, once that water reaches 212 degrees, it's going to begin to boil, and the steam will come off. Okay, it's going to hold at 212 because it's already boiling. If I want to maybe get that water to 230 degrees, what I'm going to have to do is get a pot that's called a pressure cooker where I can actually screw the lid on and create a pressurized system. And now, because I have pressure added to this environment, I can heat the water. When it reaches 212 degrees, it won't boil because of the pressure. Okay, so now I can actually get the water to be hotter than 212 degrees, but not boil because I've added pressure. Okay, so when you add pressure to something, you can change the melting point, the boiling point, or the freezing point of a substance by adding enough pressure. Okay, so these rocks are so deep in the earth and under so much pressure that the heat can get very extreme, but they don't melt. Because remember, if they melt, then we would call them magma again. Okay? Since they don't melt, they just go through a change and they become a metamorphic rock. Now, if that metamorphic rock continues to get pushed into the earth, eventually the temperatures will become so extreme that it will melt. And once it melts, then we're back to where we started, back to magma, back to molten rock. Okay, so at no time did we destroy any matter, we simply changed it. Okay, so this is one pathway that a rock could take, and these are the processes that make each of them. So what you need to kind of try and remember, obviously, are the names of the rocks, certainly, but you really need to tie the process to the rock. Okay, so cooling and hardening to igneous, heat and pressure to metamorphic. Okay, now I also talked about how this is not set in stone, no pun intended. This is not set. This pattern is not set. Location will change this sequence. So possibly we could go from magma that cools and hardens and forms an igneous rock, and that igneous rock could literally get forced right back down deep into the earth, and it could remelt. That rock could get pushed down into the earth, but have enough heat and pressure that it goes directly from being an igneous rock, is subjected to enough heat and pressure that it becomes a metamorphic rock. Okay? Maybe this metamorphic rock that's buried deep in the earth for whatever reason gets thrust out onto the surface of the earth. Therefore, it starts to get subjected to weathering and erosion and becomes sediment. Okay? Maybe this sedimentary rock gets shoved down deep in the earth, not enough pressure, so instead of becoming a metamorphic like it did over here, it melts and becomes molten rock. Okay? So location is going to determine where this all happens. And a rock can literally go from anywhere on the rock cycle to any other location at any time based on its location. Down deep, more heat, more pressure. Up near the Earth's surface, much more opportunity for weathering and erosion. And again, the key for you is to, for example, if I were to say to you, heat and pressure, you should immediately associate that with metamorphic rock. If I were to say to you, weathering and erosion, you would immediately associate that with sediments. Compaction and cementation to sedimentary rock. So what you need to kind of do is match the process to the rock type. Okay? Simply by looking at this. So every time you draw an arrow from one rock type to another rock type, you need to make sure that you know the process that's involved. So if I draw an arrow to metamorphic, I immediately write heat and pressure down. Okay? So that is the rock cycle. Okay? No set pattern, true cycle, no matter is ever created nor destroyed. And if you need anything, okay, you can kind of pause the video and kind of get any missing parts of the video by looking at this sheet. And this again is the rock cycle 10.1 in your textbook.